So, well, hello everyone. Thank you to be here for listening to me. I'm going to speak about our joint work that I did recently with Fabio Pasquale and Giuseppe Rosolini in Genoa. And actually, I mean, the results I'm going to present do not have a direct relation with the work of Eric, actually. But the interesting thing is that this whole work starts with the observation that the equality predicate, or whatever you want to take as equality, is not needed to construct setoids. I mean, whenever you have a setoid construction, you can describe it and carry it out without any need of equality in your original theory. And this observation has allowed us to prove that you can regard logical theories with equalities as coalgebras over theories with just conjunctions. And the interesting fact also is that the comonad that is giving this coalgebraic perspective is actually the setoid construction. I will show this explicitly. Yeah, so we'll present these results using Lovier's notion of doctrine that was already introduced by Benno, and also Millie mentioned them. And yeah, I mean, they're quite an important tool if you want to take an algebraic approach to logic, say. And yeah, and then in the second half of the talk, I'm going to lift these results to the case of non-faithful fibrations. I mean, doctrines you can regard them as faithful fibrations, and so we're dropping the faithfulness condition in the second half, and the first half is based on this paper that has just appeared in the JPA. So let me just say that I mean, my whole work for my PhD was I mean, the main motivation for my PhD work was actually given by the setoids and the study of the category of setoids, and yeah, so they had a central position in my work with Eric, and they were like a topic that often arose when we were discussing mathematics. So yeah, I'm very glad that I'm able to present some results that like follow from this taking this setoid perspective, but yeah, they are not they're not like immediately within the scope of quotient completions. So yeah, it seems that this setoid perspective can be fruitful also for things which are not just quotients. All right, so let's get started. A doctrine is just an indexed poset over a category with finite products. So formally is a functor like that. So Benno defined them as pseudo functors into preorders, which well, I agree that that's actually a better definition, but for the sake of this presentation, let's take this stricter version. So yeah, well, a very simple example is just if you take C, the category of sets, and the posets are given by the posets of subobjects, then from every logical theory you can cook up a doctrine where you have context and well, the fibers are given by the Lindemann-Tarski algebras. And for every category with finite limits, you have the subobject doctrine. And actually, if you just have finite products but only weak pullbacks, you can still have a doctrine by taking the the fibers to be the poset reflections of the slices. Yeah, this is the central example that I was referring to before. When you have a dependent type theory with unit types, sigma types, and identity types, you have a category which is defined like this. Is the same category that Mille introduced before actually, where you identify two terms if they are propositionally equal. And this category is going to have weak pullbacks in general. So you can consider this doctrine of weak subobjects on it. And this is the doctrine that you can use to describe the total symptotic model that that Eric considered in his last paper, for example. But you can also take, for example, the doctrine of H props, or like n types for any n, but you still need to take a poset reflection, of course, because you want to land in posets or preorders, but still. And this was the construction that Mille was describing. You can also start with like a primitive notion of proposition, and you still get a doctrine out of it. And yeah, of course, in the case of H props and the type of propositions, especially if they are like explicitly proof irrelevant, by taking the poset reflection, you're not losing that much. But in the first case, there is some more information that is missing. Okay, so let's see some the kind of doctrines that we'll be dealing with. So we say that a doctrine is primary if it corresponds to a theory with conjunctions. So we have that the fibers are in semilattices. And then the doctrine is elementary if this reindexing along this like parametrized diagonal has a left adjoint. This is formulated very much in the style of Lovier's adjunctions. And yeah, and these adjoints, they have to satisfy the Beck-Chevalier condition, so they have to commute with substitution, and they have to satisfy this Frobenius reciprocity, which is saying that is interacting well with products, with the products in the fibers, the conjunctions. Right. So yeah, right. So one thing is that when you have a description of something that is supposed to be a theory with equality, you want to know what the equality predicate is. And so for elementary doctrines, there is this well-known characterization that is saying that a doctrine is elementary if and only you have this predicate in every fiber over a product of an object with itself. That is, so this you can regard this as a binary predicate, which is reflexive, substitutive, and productive. Yeah, in this case, the left adjoint on a predicate alpha is given by this formula here. And so these guys, they will appear later on, of course, also. Right, so let's move on. We have, of course, a notion of morphism of doctrine, which is basically, if you want, a translation of the language together with an interpretation of the logic, which is the natural transformation between the fibers. And then you can form, of course, categories of doctrines. You have, well, in the case of primary doctrines, you want f hat to preserve the finite means. And in the case of elementary doctrines, you want f hat to also preserve the equality predicate. And then you can also define more like richer doctrines, like the first order ones. Yeah. And you also have a notion of two-morphism between doctrines. So these are given just by a natural transformation between the underlying functors of the one morphisms. But these have to preserve say the validity of the model. So we can really regard two morphisms as like a translation of the language interpretation that preserves the validity of the interpretation itself. And in this way, we can make these categories into two categories. And yeah, regarding these two morphisms, let me just say that is an observation by Pino Rosolini, that as soon as your theory is classical and with equality, these two morphisms are, in the case of like the syntactic category and the power set doctrine. So in the case your one cells are like standard models a la Tarski, then in this case, the two morphisms are precisely the elementary embeddings. And this explains to me at least why these are the only morphisms that classical model theorists are interested in, or almost the only ones. Okay, but this was just a side note. In order to, well, to speak of setoids is of course natural to consider equivalence relations in a doctrine. I will stop with the definition soon, but I think this is going to be the last one. So yeah, you have like an equivalence relation in a doctrine is what you would expect. So it's a binary predicate that is reflexive, symmetric, and transitive. And you have a corresponding notion of a quotient, which is given by an arrow in the base category that basically is mapping related elements to equal elements. This is again the equality predicate, and it is required to be initial. That is, for any other arrow that preserves the relation, there is a unique arrow from Q into B that makes the triangle commute. And you can form this as a two subcategory of elementary doctrines. And yeah, and well, you need to take morphisms that preserve the quotients. And in this way, we can, well, we have this forgetful functor, which has a left adjoint, as shown in this paper by Maietti and Rosolini. And so this left adjoint can be combined with another adjunction to get the elementary quotient completion that Mili was talking about before. Because well, here this construction is actually this sub Q is only part of the standard setoid construction, because it's not identifying the arrows. So here is a typo actually. So you should say that a doctrine is extensional if for any two pair of arrows they're equal if and only if they are propositionally equal. So this second F here should be G. And yeah, you have this left adjoint here, and the composite of the two is the elementary quotient completion. And this sub X is just quotienting out the arrows in the base. It's doing nothing more. So this elementary quotient completion is like the basic theoretical description of the setoid models for dependent type theories. I think that in this way you can also describe the models that use partial setoids, like Hoffman's, for example, using the if you want trivial observation that every partial relation is total on its domain. Then you can just can have another doctrine where the total relations are precisely the partial relation of the one you started with. So yeah, in this sense, it's really like unifying all the various quotient completions, the various setoids constructions that one can consider. So let's have a better look at this sub Q construction. So it has to define a new doctrine, which is this E sub Q, and its base category is given by pairs of an object and an equivalence relation on it. And the functions, so the arrows are just the arrows from the original base category that preserve the equivalence relation. Let's say that they are extensional. And then the fiber over a pair A raw is given by the descent data, what are called descent data, that there is all those predicates that satisfy this condition. So you see if this rho were the equality predicate, this is precisely the substitutivity condition. So this implies in particular that every predicate is a descent datum for the equality predicate. So you have this equality, and it follows that you have an embedding of your original doctrine into your doctrine with equivalence relations. Right, and in particular, you get an elementary doctrine where the equality predicate on a rho is given by rho itself. That's very simple. It's precisely what you would expect. But yes, as I said, as you look at this definition, we're not making any use of the equality except for defining the embedding. So by starting with a primary doctrine, we can get exactly the same except for the embedding. So we know that we land in an elementary doctrine, and as shown by Fabio Pasquali in this paper, this gives rise to a right adjoint now to the forgetful functor from elementary doctrines to primary doctrines, meaning basically that if we have a model of a theory with equality, if we have an interpretation of a theory with equality that does not interpret equality, then we can always lift it to another interpretation that preserves the equality. Now, the new result that I want to present, so the first one that I wanted to present you, goes as follows. So since you have this adjunction, you can consider the comonad generated on the primary doctrines, and you have a canonical comparison functor between the category of elementary doctrines to your category of coalgebras for this comonad. And right, so here is the comparison functor, which maps an elementary doctrine to itself together with the unit. So the unit here is like giving the co-free, or sorry, no, that's not the co-free, but it's it's exhibiting the elementary doctrine as a coalgebra, and the co-unit is just forgetting the additional structure that you have on EQ. And so what happens is that if you have what should be a coalgebra map, but you only know that it is actually a coalgebra for the co-pointed and the functor, then that's actually enough to conclude that the doctrine you started with is elementary. And then in this case, your map G has to coincide with the unit of the adjunction. So what happens here basically is that this unit here is picking out for every A the equality on A, you see? So it follows in particular that the K here, that's another typo, is surjective on objects, and moreover the comonad is coalgebraic. And in this way is that not difficult to conclude that the two functor K is another typo, is an isomorphism actually, not just an equivalence, but an isomorphism. Right, so this is the first thing I wanted to show you. And so how much time do I have left, Henrik?
Oh, about 20 minutes, I think.
Oh, that's cool. Excellent.
Yeah, well, that's including questions.
That's okay. Yeah, I imagined. Yeah, but that's fine. Okay, so we can have a look at this diagram. So this is just to recap what we've seen so far. So we have these two adjunctions, and yeah, what I just said is that we have this comonad T and its category of coalgebras, and the comparison functor is, well, it's actually an isomorphism. Yeah, you also have a canonical monad here, which actually, I mean, the unit for this adjunction on the right is the same of the unit of the adjunction on the left. And in fact, the two adjunctions, they give rise to the same monad on ED. And you can look at the pseudo algebras for this monad. And you don't look at the algebras, but at the pseudo algebras, because then the pseudo algebras are equivalent to the elementary doctrines with quotients. This was shown by Davide Trotta in his PhD thesis. And right, so basically using these two equivalencies, we can recover the two top adjunctions from just the comonad T as coalgebras and pseudo algebras for like these standard constructions. Okay, so this is looks very nice, and it's as I was saying before, using these quotient completions of doctrines for dealing with setoid models of things like the minimalist foundations, where you have your propositions which are like which are not types. So by doing this positive reflection, you're not losing that much. But when doing the setoid construction in Martin-Löf type theory, you perhaps want to keep more track of the kind of information that you have in the types as propositions. So it might be a good idea to move to fibrations instead than indexed posets to start with. So let's well, the definition of elementary fibration is pretty similar. You still have need to have these left adjoints to reindexing along parametrized diagonals, and they have to satisfy Beck-Shevali and Frobenius. But you can equivalently state instead that or require that there are co-Cartesian lifts over these parametrized diagonals. And moreover, you want these co-Cartesian lifts to be product stable and pairable. These are two conditions which mimic the Beck-Shevali and Frobenius in the case of co-Cartesian lifts. And actually, I'll be using this second definition, which I find it a bit more convenient to work with. So let's look at some examples. So of course, every elementary doctrine is an elementary fibration, or gives rise to an elementary fibration. The codomain fibration for a category with finite limits, that was more or less as before. The equality predicate is the diagonal. Now, if you have an orthogonal factorization system that has, well, you need some stability condition on E, but yeah, nothing very demanding, and you get that the sub-codomain fibration is elementary as well. But yeah, the interesting thing is also that, if you start with an algebraic refactorization system instead, you don't have only like full subfibrations of COD, but also non-full subfibration. And in particular, if you look at the algebras for the monad on the right functor, then you will find out that this fibration is elementary as well. So this in particular means that being elementary is perhaps not so directly related to proof irrelevance. And yeah, so that's quite new to me at least. All right, but let's go on. So what happens in an elementary fibration is that for every object in the base, you have a co-Cartesian lift of the diagonal. And using this co-Cartesian lift, you can basically show that this object IX carries the structure of a groupoid, except that it's like X is the set of objects and IX is the set of arrows. So they are living in different categories actually. So it's not really a groupoid. It's more like a groupoid structure over X or something like that. But anyway, so let's give them a name. Say that for a fibration with finite products, an F groupoid is given by a list like this, where you have arrows for the identity, the inverse, and the composition that satisfy the groupoid laws, indeed. And note that these arrows are required to be over certain lists of projections, which basically is describing their behavior. And right, then you have also a notion of morphism of groupoids, which is precisely what you would expect is given by a pair, one in the base and one in the category E, and in the total category. And these are required to preserve the identity inverse and oh, this is supposed to be comp, sorry, of course. And yeah, then you can form a category of these F groupoids. And in particular, when you start with an elementary fibration, then the groupoid, the F groupoid that I described before, is going to be the initial one. This should be no surprise. And yeah, you use the fact that this arrow here is co-Cartesian to show initiality. All right. So we also have a monad that describes the actions of these groupoids on the fibers. And this monad is very useful for describing the descent data for this groupoid, because now we want to build a fibration over these groupoids in the same way that we built a doctrine on the equivalence relations before. And recall that the fibers of the doctrine were the descent data. So here we want to get something similar to this descent data. And this something similar is given by the algebras for these monads, which I don't have time to tell you what it is exactly. But they are not all algebras, but only those over certain objects, which again, I don't have time to tell you what they are. But yeah, so this category here, this category, this is going to consist precisely of the thing you expect to have. That is arrows of this form over the second projection. And yeah, and the thing is functorial in the sense that if you have a morphism of F groupoids, then you get a morphism of monads. And by this morphism of monads, you get a reindexing functor between these descent categories. And you can thus form a fibration where, yeah, the fibers are this descent data and the reindexing is given as before. And in particular, if you start with F being this trivial fibration, then your F groupoids are going to be groups, and your descent data over G is going to be precisely the topos of G sets. So let's call this fibration the fibration of F groupoid actions. And now what we have is that this is, well, this is underlying a comonad on fibrations with products, in the sense that this function mapping a fibration to the fibration of F groupoid actions leads to a two functors, to endofunctors on the category of fibrations with finite products. And this functor underlies a two comonad, and such that a fibration is elementary if and only if it has a coalgebra structure. So this does not yet fully generalize the previous one. We have not shown an equivalence of categories, but yeah, we're very close to it. I mean, we haven't. I haven't written down its comonadic just because we still have to check some details, but I see no problem in that actually. So let me conclude with a quick remark on setoids actually, because the previous discussion suggests that we can as well consider the same structure as before, but just dropping the equalities, right? And we end up with what I will call an F setoid. And the same functor that we had before works again. It's just that now it's not a monad anymore. It's just an endofunctor. But you can still get the category of algebras and the category of descent data as a subcategory, and you get also fibration in this way. And yeah, what I expect, in fact, shouldn't be difficult to prove from the previous result. I mean, using the same techniques, that this function now also leads to an endofunctor, which underlies a comonad 2 on this category of fibrations. So let's say that fibration together with a coalgebra for this comonad is a setoid fibration. And well, we know that that's pretty straightforward, that elementary fibrations are setoid fibrations. And I want to conclude by showing you an example of another setoid fibration. So there is this construction in this beautiful paper by Vandenberg and Moerdijk, which I find it actually as a very nice description of the setoid construction in intentional Martin-Löf-type theory. And basically, it's a construction that starts with a path category. I'm not giving you the definition, but consists of a class of weak equivalence fibrations satisfying what you would more or less expect. And so what they're doing is describing the setoid construction as a homotopy category on another path category, this EXP. Yeah, so what it turns out is that this EXP is precisely a co-free setoid fibration, in the sense that if you take the previous construction and you apply to the fibration of fibrations of the path category, then you get precisely the fibration of fibrations in this EXP. And yeah, I hope that perhaps in this way one could find, for example, a universal property for this construction, which, as far as I'm aware of, still something that we don't know. All right, so I'll stop here. Thank you very much.
Thank you, Jacopo. And questions?
Yes, so hi, I have a question.
Yep. Hi,
so thank you for your talk. So my question is, so if I understand right, you claim that elementary doctrines are coalgebras over primary doctrines, right?
Yes.
They should be algebras as well for a monad.
Why is that?
I mean, it's more a question than an affirmation, but I guess they would be. Is this the case?
No, not that I'm aware of, actually. I mean, the algebras for that, I mean, actually the pseudo algebras for that construction are actually the elementary doctrines with quotients.
Okay, but I'm talking about the T coalgebras. I was wondering whether they are equivalent to the M algebras for some monad M on primary doctrines. Which would be freely adding equality in some way.
Well, I'm not sure, actually.
Okay, I mean, my naive guess is simply you freely add equalities and everything should work fine, but I mean, this could easily fail.
Yeah, right. I mean, what happens here when you freely add equalities is that you actually are co-freely adding them, at least if you, I mean, if you're using this setoid construction. So if adding equalities means considering equivalence relations.
Yes, and here you are co-freely adding equalities.
Right.
I agree with that.
Yeah, and if you instead, yeah. So if your question is there is another construction that instead freely adds equalities, then my answer is I don't know.
Okay. Okay. No. Yeah. Thank you. No, I guess there is one, but I might be wrong.
I don't know.
And we have two more questions.
Thank you.
Two more questions. The first is from Steve Audi.
Thanks, Jacopo, for that nice talk. You had this situation where you have groupoid structure up in the fibers, but you don't really have it you don't have a groupoid in the base.
Right. Yeah.
And have you considered adding Levere comprehension in the sense of
Yeah,
hyperdoctrine?
actually, yes, that's an excellent question, and is in fact the next step that that we would like to take is to look how these interact with comprehension structures in that.
Yeah, great. It's a way of kind of putting in a context extension operation.
Yeah.
Okay, great. Thanks.
Yeah. Also, I wonder how much will that make it close to the identity type, for example.
Next, Thorsten, and then Millie after that.
Yes, I was just wondering, in type theory, we've looked at a sort of translation from a type theory which has actually sort of an extensional equality into a type theory which is using setoids. I give 2 links in the chat. So I just wonder whether this is related to the construction you're describing.
Yeah, actually, that's very possible. Yes, but I don't know. I have to say I don't know your papers, so I haven't.
So I give some links. The links are in the. And recently, actually, we also tried give a construction of a universe that's not yet published.
Oh.
And for the universe, we actually need an equality in the theory you start with. Yeah.
I see.
Yeah.
So actually, my experience with having or not having the equality in the underlying theory is that this is actually so let's say that the main thing that I could notice, at least, is that this gives you a choice principle in your completion. So like in the case of the exact completion, the embedding is providing a projective cover. So it's giving you enough projectives. So it's like having the presentation axiom. But if you do the same construction without, I mean, this is not something you can do with the exact completion. But if you take the quotient completion of something that doesn't have equality, then you don't have the embedding. It's something that
yes, sure.
I mentioned before, and yeah, so it's like there is a bit less of like choice principles that you can have. This is the comment that I can make on that.
Okay. Okay, thank you.
But I'll check out your papers. Let's see if there is something in common.
And then Millie for the last question.
I was wondering whether there is a connection with this notion that you considered about groupoids with you talk about actions. So if there is a connection with the dependent setoids, the one I mentioned in my talk.
The setoid families. Yes.
An abstract view of this action of where the setoid is taken as a groupoid and
yes, but I mean these setoid families, they are I mean they are precisely the kind of families of setoids that you will get by looking at extensional functions. So if you consider the set family associated to an extensional function, that is precisely a setoid family. And conversely, you can regard every setoid family as equivalently an extensional function from.
The function, yes. But is a presentation of it which is a splitting, let's say, that allows a splitting in.
Yeah, right. Yes.
So do you have any abstract rendering of this in this with this work?
Well, actually, I think that where is it? Yeah. So the descent data here of this vibration of setoid actions
should be that.
Should be, yeah, consists precisely of those kind of families.
Yeah.
And actually, these are I don't know if Benno that rings a bell, but those should be the I think you call them stable vibrations in your paper. homotopy exact completion. So those such that if you have a loop in the base and you can transport along that loop, then that transport is actually irrelevant on the proof that you pick in the base.
Proof irrelevant groupoid, yes.
Yeah, no, I mean it's not the groupoid that is proof irrelevant. It's the family that is irrelevant with respect to the action of the groupoid.
Ah, yes, yes, yes.
Or is the action that is irrelevant, actually, maybe. Well, yeah.
Okay, thank you.
Okay, let's thank Jacopo again.